Okay, so 3.3, so interpreting and sketching graphs. So a lot of these functions that we're doing, or all of them really, right? We can sketch these things out. So we're gonna come back to interpreting some of these graphs and what's happening. So graphs are really good at communicating like what's happening in the world, right? And sometimes when we get like a straight line or a curve, which was the issue yesterday, or like a flat line like that, those tell us things, right? Those tell us things about what's happening there. So graphs to communicate. So a graph is an effective way to show a relationship, right? Show the same graph on the other one. Other kinds of graphs, right? You guys have been doing this in science right now, where let's say that this was a distance time graph, then you guys have probably seen that a steeper line, right, this would have a bigger slope. That thing's going faster. And like I was saying before, it would be covering more distance over a shorter period of time, right? It's covering more and more distance as it's going on, so it's moving faster. Where this one's not moving as fast because it's not covering as much distance as time goes on. Does that kind of make sense? Yeah? Okay. You can do it the other way too, where if this was like a distance time graph, where if it was, again, more of a slope, that thing's still moving faster, it's just moving in the other direction. Okay, and this one's moving slower if it's going down like that. Okay, I made this into a distance time graph because a lot of times that's easier to kind of picture with rate of change. But this is really like any rate of change question. So this could be how fast a pool is filling up, right? So this could be like volume over time, right? So maybe the volume of the pool is filling up with this sort of a rate or something like that, right? So it can be any rate of change. And a rate of change is just how things are changing over time. Yeah? Okay. Horizontal line would mean that there was no change. So again, if this was a distance time graph and we had a flat line going across like that, well then that's telling us that the distance, right? Because distance is up and down here. The distance isn't changing and time is going by. So this thing isn't moving. It's stuck at whatever distance we were. Like if this was 5 meters, then this thing was like stuck at 5 meters as time kept going past. You guys agree with that one? You guys have literally, I know you've been literally doing this in science, so. Okay. Sometimes relationships can be shown as curved lines. So this is a big part of math, right? When we get into 20-1, 20-2, we do a lot with these curved lines. We do like what they're called parabolas in this case. And then in math 30-1, we'd have more like this one, like exponential growth and all that kind of stuff. All right, so looking at this question, this is like an interpreting one. Which point on this graph represents a person? And it says, which person is the oldest, and what is her or his age? So what point on here would represent the person that was the oldest? Yeah. Do you guys see how, like, this is us just like figuring out our axis here. Here, maybe if you can't see this. If we look at our axis here, age is going this way. So the person who is the oldest, if I'm just looking at this one, I'm just looking for like, the one that is farthest to the right. So that would be G in this case. So this would be G. And how, not a 6, G. And how old are they? 18, right? It goes up 16 to 20, so this must be 18 in the middle. So this person is 18 years old. So how old is she? She's 18. YR for years. Okay, which person is the youngest? A. So this person's 0. So on our graph, right, this probably isn't that this person's actually 0. Like it's not that they were like literally just born. I think we're probably calling everybody that wasn't up to 1 yet would be classified as 0, right? So, but anyway, that would be person A. And maybe they're 6 months old or something. But yeah, for us now, they're 0 years old.
They don't exist yet.
Yeah. All right, which two people have the same height?
B and C.
B and C, yeah. So B and C, they're different ages, right? But they are both at 100 centimeters tall. Oh, I gave that one away. So yeah, B and C. And they are 100 centimeters tall.
centimeters.
Which two people have the same age?
E and D.
4 and a meter tall.
E and D.
Centimeters.
Huh?
So E and D, and it says what's their age? They would be how old there? 10. They're both 10 years old. All right. Which of person B or C is taller for his or her age? So which one do you think? So which one? B is taller for the age, right? Because they're younger and they're still the same height. So B is going to be taller for that age. Okay.
A 0-year-old is half a meter. That is completely correct.
All right. Let's look at this one now. All right. So the graph shows the distance a rock climber is from the base of a cliff as time passes. Using the words climbing, resting, or descending, describe what the climber is doing during each segment shown. So again, for the sake of time here, I'm not going to like actually write them out, but I think we can just kind of talk about it. So during this section here, what's happening? They're climbing, right? They're going up the mountain at a constant rate there. What about from A to B? What's happening there? Yeah, they're resting, right? As time keeps going by, their distance isn't changing, right? They're stuck at that one distance right there. Should probably use something other than red, eh? Okay, what's happening from B to C? Climbing. What's happening from C to D? Yeah, and that was really fast. It looks like they fell. I don't know. Yes, they went down pretty quick. They recovered from their injuries, it looks like here, for a while, not moving. And then they were kind of injured, so they didn't go up very fast anymore. Right? There was like less steep, so they're going a bit slower than they were at this stage.
And then you just stop.
And then they got to the top of the mountain, maybe, or they just stopped. Yeah.
So with
Okay, is there more than one interpretation of the climber's action during the times indicated by A, B? Yeah, there is, right? Like I said on this one, maybe they fell. Maybe they just like jumped down like quickly. Like I don't really know what happened there, but they did get closer to ground level or down to the base at that time. Yeah, you guys could be creative, right? Okay. For any section that you listed as climbing, how would you change the graph to show that the person is climbing faster? So let's say, so if I wanted to go from D to F or whatever and show that they're going faster, what would happen to that line? It'd be steeper, right? So it'd be like a steeper line.
That's a steep line.
What would you add to the graph to show the climber's return to the bottom of the cliff?
Descending.
Right. Let's say they fell all the way to the bottom. That'd be pretty fast, right?
And plummet to the shark. Bro,
That
that's
was
so
the
bad.
diagonal. I feel like they would be. No, they just go.
It'd be straighter.
All right.
Is it possible for
So on this one, work in pairs. Match each graph with a situation from the list. Explain your choice. Suggest titles for each axis to show the quantities being compared. So actually, yeah, I'm going to pause it. Can you guys, just with the person, or just even think about it? Let's go through these. So it says the temperature of a cup of hot chocolate over time.
Graph C.
You guys thinking graph C? So if this was temperature, right? So then this would be temperature, and this would be time. Here, TT, maybe I'll write temp. Well then, yeah, maybe that might be a good one, right? So it loses its temperature pretty fast to begin with, but then kind of holds on to it, you know, that last little bit. Yeah, like at the end of it, it won't change as fast, but when it's really hot, it'll change pretty quick at the beginning, right? So good one. Okay, a car accelerating to a constant speed. This one might be a little bit tougher. D, we think.
no, it's E. No, because it says to a constant.
So if it's a constant speed, it doesn't go any faster.
All right, let's think about this one. So a car accelerating to a constant speed. Let's say that this wouldn't make any sense if this was distance and this was time. But what if this was speed and time?
Yeah.
Yeah.
That would make a bit more sense, right? Because if it's accelerating, right? Acceleration on a velocity time graph is a straight line. Because what this means is that it's velocity, right? Maybe it was going 1 meter per second, and then 2, and then 3, and then 4. Maybe it's going, like its velocity is changing. And a changing velocity is acceleration.
And then it hits the speed and then it just.
and then it hits a constant speed. So then the speed plateaus and just stays at like 10 meters per second
Yeah.
or something, right? So then it stays at that constant speed. Yeah? Okay, so that, here, let's write those down. So that would have been, so B was B. We said this was A.
Yeah.
Here, let's do it the other way around. Let's go on these ones. So the temperature of this one was graph C. And then the car accelerating into a constant speed, we'll say was graph B. Okay, the distance a person walks during a hike. Yeah, that could be constant, right? So if time keeps going by, then this was distance, then that'd be just the distance they cover there. So this would be graph D. Graph D. And then this one might not be that intuitive. The height a soccer ball kicked across the field.
That's definitely A.
Okay, let's, because this will help you guys, I think, in physics too, right? Like you guys will be seeing this one. If this is time and this is distance, or like height, right, in this case, then you can think at the beginning, this thing is going up pretty sharply to begin with, right? It's covering, this is like, so if I threw this thing up in the air,
Do it.
Do it.
right? So if you throw this thing up in the air,
Just do it. Just do it.
it's moving really fast to begin with, right? It's moving really fast to begin with, so that's this beginning.
Slows its speed when it hits.
And then it comes to a place where it gets to the top, right? It gets to the top,
Just
and then
missed
it comes to a stop and starts coming back down again. So it comes to a stop at the top, and then it starts coming back down again. Does that make sense? Okay, so this would be graph A. All right. All right, if you're watching the video, we're ending it right here, and we're just gonna do some questions there. So.